Hey everyone, this is Physics 2211 Lab 3 about a black hole. Let's get into it. So as an introduction, the purpose of this lab was to, one, find the mass of a black hole using a simulation between a star and a black hole. And then with part two, with similar simulation, there was a black hole, a planet, and a spaceship, and the goal was to find the velocity, the initial velocity of a spaceship that would draw the spaceship near the black hole without hitting the planet or the black hole. And so you can see the findings right below. Here are some fundamental principles, and we'll start with Newton's second law, where F net equals change in momentum over change in time. And so from that, we can make a velocity update formula and a position update formula. Some other fundamental principles are the parallel and perpendicular components of the net force. So the parallel component goes in the direction of motion, and hence it will only change the speed of the object. And then for the perpendicular, it is in the perpendicular direction of motion and only changes the direction of the system. And so the parallel component is p hat and the perpendicular is n hat. Here is gravitational force, which is defined by negative gmm over r squared times r hat. So it's multiplying the masses and the gravitational constant together, dividing by the distance between the two masses, and then multiplying it by a unit vector r hat to get the direction of the force. And it's negative since it is an attractive force. Here's some free body diagrams. You can see part one, it's modeling the black hole and the star. And then in part two, it's modeling the black hole, the planet, and the spaceship. Here on the left, you can see some constants for part one in the code. And then on the right, pretty much we're just finding F net and then using that to find the black hole mass. So here is some of the results of simulation part one. You can see the net force in the parallel and perpendicular and the mass of the black hole. And so if you take a good look at the video, there's arrows to show the perpendicular, the parallel, and the net force. They do a good job of showing it. And so as it goes around, you can see that the arrows grow smaller further away from the black hole, meaning the net force is smaller. There. So some possible sources of error is that there's some rounding during each iteration of the loop and in the gravitational constant, so that can cause some error. So for part two, here's some of the initial stuff, and then down here you can see the speeds that I guessed, and they did a pretty decent job, as you'll see in a second. So up here you can see some more calculations of the net force on the planet and the ship, and then as you can see in this code, this changes the velocity and position of the planet and the ship. So here you can see the other simulation with the ship's initial velocity right up here, and then the closest it gets is this number right here, which is pretty far but pretty close to a black hole. So I'm just going to do a little recap of part two simulation. So the initial velocity is moving up and to the left, and it's actually moving more left than up since x velocity is greater, and then the ship experienced the greatest force of gravitation when it is closest to the black hole. And then the ship escapes the black hole system because it picks up speed as it moves toward the black hole, and then it rounds it and has enough speed to escape. So this question is asking what's the difference between the net force and its components and the rate of change of momentum and its components. And actually, since the net force and the rate of change in momentum are the same, there is no difference between them. This question asks what initial velocity for the spaceship would allow it to orbit the the black hole instead of leave it. And so I toyed around with some speeds, and I got these right here. So the x had to be less and the y had to be more, and it worked out pretty well.